I am so happy! The price of my bitcoins went up by 20%. Time to sell. Perfectly safe. Absolutely no way I'm getting hacked.
You don't want this to happen to you, right? Well, that's exactly why many major cryptocurrencies use elliptic curve cryptography. Now you might be wondering, what is ECC cryptography and why is it used to protect such important data? Well, that's exactly what Professor Crypto will now explain.
ECC cryptography protects your data using elliptic curves. Here's a few examples of what they look like. They have the general equation y squared equals x cubed plus ax plus b. ECC cryptography uses two keys, a private and public key. The public key is a known value. The private key is the value multiplied to reach the public key and is only known by its owner. Think of it like this. I have this yellow paint and blue paint. These would be my private keys. Everyone knows the final value, which would be the green paint, but they don't know which colors to mix in order to create it because they don't have the private keys, my buckets of paint. ECC cryptography creates these keys using points on an elliptic curve. The private key is a large random secret number, which in the case of Bitcoin is 115792000. Oh gosh, it's a really long number. Whereas the public key is that number multiplied by a base point on the curve through a process called scalar multiplication. We will need to create a new form of mathematics to explain the addition and multiplication of points on an elliptic curve. This is known as a mathematical group. A group allows you to combine objects together in a way that is predictable and constant. Let's say we want to add 2 points, P and Q. We define the addition of points by drawing a secant through both points, then reflecting the new pointer across the x-axis to get P plus Q. We can use many of these point additions to create scalar multiplication. We do this operation k times, where k is our private key. Scalar multiplication is computationally easy to perform. However, to determine k using the base point and the public key is incredibly difficult. This is due to the elliptic curve discrete logarithm problem, or the ECDLP. The reason you can't just rearrange for k is because with elliptic curves, point multiplication is simple, but the reverse operation is not division and is rather discrete logarithms. Given p plus q, you cannot find p and q. Here's a simple analogy. Let's say I have a secret recipe for microwaving my special popcorn. It must be microwaved for precisely 130 seconds. No more, no less, or else it'll explode. Now only I know how long to microwave it. The 130 is the private key, which only I have. It would be nearly impossible to determine how long it was microwaved for, given the public key, which in this example would be the popcorn. Somebody remind me to stop this later. Let's say we have an elliptic curve, E, defined over the finite field F, F being all points that satisfy the elliptic curve. This field prevents values from exceeding the limit because the curve cannot be infinitely sized. If a point leaves this finite field, it will be recalculated back into the range. N will be the number of points on the curve. Now, from our equation, public key Q equals K times P, K is defined as the repetitions needed to encrypt P in order to generate the public key Q, where P and Q are both elements of the finite field and K is an element of the natural numbers. The integer K is known as the discrete logarithm of Q to the base P, written as follows. Note that this is not a normal logarithm, as it exists only in the mathematical group. Without quantum computing, the only way to derive K from P and Q is by brute force. However, it is so incredibly unlikely, seeing that the total number of possibilities is 2 to the power of 256. This takes about 10 to the 40th power years with modern technology. That's from now until the end of the universe, times 10 million, millions. That is precisely why ECC cryptography is essential for the protection of valuable information. Wait, don't stop the video, I forgot to explain the...
Well said! So if you want a more secure way to protect your data, then click this link to download the newest version of ECC encryption.
This seems so much safer.
Ah!
I can't believe I just got scammed by an AI video.